Welcome back to this antenna design tutorials. So in the last video, we have discussed about antenna basics. In this second video, we'll discuss about basic antenna, that is dipole antenna. It's a simple antenna which we can easily design. So as name suggests, it will have two poles, meaning to say two cylindrical wires of total length lambda by 2. Implicit meaning is each half section is having a length of lambda by 4. So at certain frequency, a dipole antenna consists of two conductors of length lambda by 4 each. So this dipole antenna is excited at the center by using a source. In simulation 2, we consider this source as port. So we'll assign here port. For this simulation in CST, we'll assign this as lumped port. In lumped port, we can define whatever the impedance we want, we can define it. So for the dipole antenna, the input impedance at the center is around 73 ohms. So this 73 ohms will assign in port definition and we'll simulate it. So for designing any antenna, as an antenna design engineer, we should know what are the specifications or what are the requirements from the vendor. If you know the specifications according to the specs, we can design. So here for this dipole antenna, anyway it will have minimal gain of like 1 to 2 dB. So here the important parameter is at which frequency we have to define it or we have to design it. So for our design purpose, I'm considering this as 2.4 gigahertz. So for 2.4 gigahertz frequency, we'll design a dipole antenna and we'll verify in the simulation. So here lambda is C by L, which is 311 divided by 2.4 E9. So 311 is because of its in mm. So if it is in meters, then we can go ahead with 38. If we calculate this value will come around 125 mm. We need a length of the dipole as lambda by 2. So the lambda by 2 value will comes around 62.5 mm. So the required length of the dipole is 62.5 mm. So we have calculated the length. So we'll just go ahead and design this in simulation tool. For this, we have to go for CST software or any simulation tool is fine. For our convenience, in this video series, we are taking it as CST as a simulation tool. So here okay, we open this CST tool. It will open with this project template. So click on the project template. It will open. It will pop up a window. In this, we have so many types of designs. So here we are designing microwave and RF components. So I'll go ahead with microwave and RF. In that, I have to design an antenna. So I'll go ahead with antennas. We'll go ahead with next. And here in this design, we are going with wire antennas. So I have selected here wire. And next, here integral equation is for thin wires. Thin wires meaning to say, if you have 2 radius for 100 megahertz antenna, then in that case, according to wavelength, the diameter is very less. So for those thin antennas, we have to go for integral equation. Their meshing will be very coarse and the simulation time will be reduced. For our case, it isn't a problem, so we can go ahead with thick wire and case time domain solver. We'll go ahead. We'll keep all these parameters as it is because we are working at gigahertz, gigahertz frequency and dimensions in millimeters. So I'll keep same thing. Here we have to define the range of frequencies. For now, I'll define it as 1.5 to 3.3. So why I have taken this much wide bandwidth, I'll explain while designing. So we'll go ahead with the next and finish. So once we have done the initial procedure, this will pop up like this. Here you'll have home window modeling, simulation, post processing, and view. For we have for this design, first we have to model the dipole. So for that, I'm going ahead with modeling. So if you open modeling, in this you will find what are the blocks I have to design and what are the operations I can do and selection process and all we'll have here and coordinate system, all these things. So here for now I need a cylinder. So two cylindrical wires we need. So we'll define here cylinder, select on cylinder and press escape. Here press escape to show the dialog box. So escape and this window will pop up. So here we have to give a name. If we are not giving any name, then it will give directly solid 1, solid 2 automatically. So this doesn't have any impact on design, but whenever we are designing for our designing purpose without getting any confusion with the boxes, our cylinders will define here bottom cylinder and it is oriented in Z direction. The radius, I can give it as 2 mm or instead of giving number, I can give a variable directly like this or I can use this variable as a parameter where I can tune or I can change or I can modify. All these things I can do by defining variable instead of going into the cylinder definition and all. So this is the best way. Then this inner radius we'll discuss whenever we need while designing the designs. As of now, for this design, we doesn't require any uh, inner radius. If you are using any hollow cylinder, then in that case, we have to define outer and inner radius. For now, we are using normal cylinder, so I'm just using it as staged. So X center, Y center, I'm taking it as 0, 0. Z minimum, I'm taking it as a gap. So I'll take this value as minus gap and minus gap minus L by 2 or length by 2. So length by 2 have to be defined in one direction. This gap is for giving that port. So for that purpose, I have given this gap value, and we can take material as aluminum. So this aluminum material already defined here. So we'll load this and then press OK. So it will ask for the radius value. I'm giving it as 2. Gap for now I'm giving it as 1. The length I have already calculated is 62.5. So I'm giving this as it is. So we are getting this half cylinder. So we can define one more cylinder here by clicking here. I'm giving one more method instead of defining here and doing all these things. You can directly go to history list here in the modeling itself. You can go ahead with copy of the last defined one and paste it here. So the same thing is repeated. You can double click and we can change this name and whatever the parameters you want to change, you can change here. Top cylinder and radius is same, but it is oriented in positive. So I'm giving it as positive gap and gap plus length by 2 and plus OK. Then these two are defined, but as of now, it is showing in components only one. We have to update it. So once it is updated, here we'll get top cylinder also, and close this. Here you will get top cylinder and bottom cylinder. There is a gap. So here I need to define port. So for defining port, I'm just selecting face of these two things, two cylinders where I have to define this port. I'm going for defining discrete port. So discrete port case, this I'm giving it as one variable Z input impedance at this port. So I'm giving it as Z and I'm pressing OK. Length cannot be 0. So here minus gap to plus gap. If you so the Z I have to give it as 73 ohms. 73 ohms. Port is assigned between these 2 points. Now it is okay. So now the port is assigned. 2 cylinders are there and our design is ready. So before going to simulation, first check at which frequency you are going to simulate. Sometimes in the initial data, we might have missed this data giving. So in that case, it won't be a problem. So background, it has to be normal, and boundaries, they have to be open boundaries. So open and add space. This is fine. So now we can go for simulating the design. So we'll start the simulation. simulation is start. So it will take some time. The design is a simple design, don't take much time. We have to wait for at least 5 to 10 minutes. So it's not taking much time, so it is analyzing fast. Take much time. Port signal. Can take up to 2 to 3 minutes, not more than that. So the simulation is done. So here we can see the S parameters. If it is exactly lambda by 2, then the resonant frequency is coming below of what we have calculated. For this design, we have calculated for 2.4 gigahertz and the resonance is coming around 2.05 or 2.04. And this is not we have calculated. And for this purpose only, purposefully, I have defined frequency range is from 1.5 to 3.3. To show this, 1.5 to 3.3, I have defined here. So at 2.01, it is getting good matching and it is having a bandwidth from 1. Say suppose 1.83 to 2.3. So we have good bandwidth as well as good matching, but not at the intended frequency. So for that, what we have to do, we'll see. And via after simulation, first thing you have to see is this. What is the S parameters of this designed antenna? After that, which impedance you have done this. For our design, we have taken the lump port impedance as 73 ohms. So we have given it as 73. So input impedance is 7. If we are using wave port, then in that case, it will calculate according to the dimensions of wave port assigned. So for certain cylinders, you have assigned a wave port. So for that case, it will calculate what is the impedance, input impedance. That input impedance will come. So that case, the input impedance might change. Depends upon the design. We have to verify whether our reference impedance is 50 ohm or whatever the impedance you are intended to design. Whether that is there or not, we have to verify. And the next thing here, you need to check VSWR. So wherever VSWR less than 2, we'll consider it as match. So here less than 2 sometimes will take, and less than 1.5 depends upon the application. So there is no specific kind of this has to be like 1.5 only, 1.2 only. That kind of requirements are not uh, not specified in anywhere, but it depends upon the application and the specifications. And the next thing you can verify here Z11. So here if you see, you can plot a real and imaginary. So where it is crossing its zero crossover point, that is the resonant frequency. At this point, you are getting resonance. And at that point, you will have impedance near to 50 ohm or near to 73 ohm, what we have given as a reference impedance. So at that point, the impedance matching is very good. This you can analyze with all the designs. Whenever we are designing these things, we have to check this. And the next is far field. The far field will show the radiation pattern what we have discussed in our first initial video. In that we have explained about the antenna parameters. In that we have talked about ba- bandwidth, impedance matching, and there are efficiencies also. So here how much efficient it is if you go to linear scale. So radiation efficiency is high, but total efficiency is 0.85 only. This is because of losses and mismatches. At 2.4, it is not exactly matched, so it is 85% efficient only. And the radiation pattern is for dipole. Radiation pattern is like this. It's like a apple. You can say this is the here the radiation pattern. If you see this 2D plot, so it is radiating in one direction only. At this point, it is null, as we discussed in the first video. And here the beam width is angular 3 dB beam width, that is 74.5, which is this one. This over this range, the beam width means maximum less than minus 3 dB. Wherever angular 3 dB beam width, that means maximum minus less than 3 dB is available, the intensity level or power level is available, that range is defined by beam. Here this angular beam width is 74.5 for this end. And so if you want to plot this in rectangular, so we can go for Cartesian plot also. So here we have only single lobe. This is from 0 to 180. If you want 180 to 180, so we need to go for this plot in 360 degrees from minus 180 to 180. So this will show at 0 you have null. One direction it is having max and null, and then max and null. So here half power beamwidth will come here. If you say here only one null is there, so first null beamwidth will be this much. So depends upon the application, first null beamwidth will vary according to the radiation pattern. This is what about radiation pattern of this dipole antenna. And our next thing is we are getting a resonance at 2.02. So for this purpose, we can simply shift it to 2.4 by just making the length reducing. So if you want to go for higher frequency, the length has to be reduced, and for lower frequencies, the length has to increase. That's the only thing we have. So here our current length is 62.5. Our intended frequency is 2.4, and current frequency is 2.02. If we take this as like 62.5 multiplied by 2.02 and divide this thing by 2.4, will come around 52.6 mm. So I'll just change this as 52.6 and we'll rerun one more simulation. What will happen? We'll just check it. This will take 5 more minutes. So after 5 minutes, we'll come to know what is the effect of length of the antenna and how to scale it to downward or to upward. All these things will come to know with this simulation. After this one simulation, we'll come to know all these things. So with one simple calculation, we have shifted our resonant frequency from this 2.02 to 2.4. That's simple calculation is nothing but, so if you go to calculator, what we have done is simple calculation. So current length is 62.5 multiplied by current frequency 2.02, and this is divided by 2.4 required frequency. So that value is given as 52.6, and the same thing I have included here 52.6, that is giving resonance at 2.4 gigahertz. So whenever you start with some simple calculations, and after all the book based equation calculations, if your resonant frequency is not the exact required frequency, then you just use this scaling option. You can shift your resonant frequency from the current frequency to the required frequency by using this simple calculation. So after this, here we'll just analyze one more simple parameter. What is the effect of this impedance Z equals to 73 volts? So instead of 73, I'll just put this value as 50, and I'll store the current results in cache, and I'll resimulate it. But this will with this analysis, after completing this analysis, we'll end up this video. so that we'll have clarity on dipole antenna, what gives which result, and in which way we have to tackle the frequency shift or impedance effects. All these things will come to know for that dipole. Further, if we have or if you have any doubts or any clarifications, we'll just resimulate all the things and we'll upload one more video for your doubts or whatever the questions you might have. Those things will answer in next future videos if you ask me questions. If you have any questions related to this, please ask me in the comment box so that I can read and I'll try to solve those questions, and I'll make one more video on those questions. We'll check the results after completing this simulation. So now here, so what happened is, in the previous case, if you see these results, it is not like a resonance shift. It is like matching shift. So for understanding this, we'll just check this Z1. Z resonance. So our resonance is not changing. Instead, it is having a matching point. Like here, impedance for this is around 60 ohms, which is nearly matching with 72. Whenever we are giving 50, the 50 can be matched up to 33 and 66 ohms. So wherever we have 33 and 66 ohms, in that range will get matching. So here, this range we see 66 is coming around to near to 2.4 and 33 is coming around 2.1. Over this range we are getting matching. So here up to this point, here we are getting good matching for 50 ohm. For 73 ohms, we are getting range as different frequencies. Here we are changing the input impedance according to your Z11 and reference impedance. The matching is like reflection coefficient S11 will be calculated. So for 50 ohm, this range of frequencies are matched, meaning say over this range of frequencies, 50 ohm matching is there. Over this range of frequencies, 73 ohm matching is there. So that's a simple implication. Whenever we are designing some design, so first we have to compare these two S parameters and Z matrix so that we'll have good understanding of the design. So we'll stop here. From the next tutorial, we'll take up a loop antenna. So thank you. Bye bye.